Welcome back to my YouTube channel. In this class, I am going to discuss about an important topic, that is Carnot cycle. You know, Carnot cycle is a reversible cycle. So, before going into the Carnot cycle, we must understand what is actually a heat engine cycle. You know, heat engine cycle is a thermodynamic cycle in which there is net heat transfer to the system and net work transfer from the system. You know, there is some heat input, and out of that heat input a fraction is converted into work output, because we know that the complete amount of heat cannot be converted into work output, because heat is a low grade energy and work is a high grade energy. And one of the unique aspects of second law is that it differentiates between energies, and it differentiates it into two categories. One is low grade energy, another is high grade energy. Heat derived from any source comes under low grade energy because it cannot be completely converted to work. So before going in detail into Carnot cycle, I must say one thing to all of you: please do subscribe to this channel, and of course like it and share it to your friends. So let's get started. So before going into Carnot cycle, we must know what is actually a heat engine. You know, heat engines are cyclic devices. Heat engines are cyclic devices. Heat engines are cyclic devices. Cyclic devices in which working fluid completes a cycle. Cycle means it returns to its initial state. You know, whenever a working fluid returns to its initial state means its temperature, pressure, or any other property, then we can say that a cycle is completed. First, we must understand what is a cycle. So, cycle means working fluid is completing a cycle. And your steam power plant can be an example of heat engine, in which the working fluid may be water and it undergoes a phase change. So, that is, the working fluid completes a cycle, then you say that is a thermodynamic cycle. So work is done, you know, whenever a working fluid completes a cycle, work is done by the working fluid during one part of cycle, and on the working fluid during another part of cycle. So during one part of the cycle, work is done by the working fluid, and during another part of the cycle, work is done on the working fluid. You know, the difference represents the net work output of the cycle. The difference, actually work done by the fluid is conventionally taken to be positive and work done on the system is taken to be negative, and the difference between these particular two works, one is work done by the working fluid during one part of the cycle, and another is work done on the working fluid during another part, and that difference is nothing but the net work output of the cycle. The difference between these, the difference between these two represents the network output of the cycle. Network output is always positive, otherwise there is no utility of heat engine. Heat engine are network output of the heat engine must be positive, because they are work producing machines. Refrigerator and heat pumps are work consuming devices, but heat engines are work producing devices, and network output of heat engine must be positive. So our objective should be to maximize the network output, and once the network output is maximum means efficiency will be maximum, because we know that efficiency of a heat engine is nothing but it measures the performance of a heat engine. It represents what amount of heat input is actually converted into net work output, because efficiency of any heat engine is defined as the ratio of net work output and heat input, heat supplied. Net work output divided by heat supplied, and it is always less than 1, because the complete conversion of heat into work is not possible. So how to maximize the net work output of a heat engine? How to maximize the net work output of a heat engine? The net work output of a heat engine or efficiency can be maximized only when we can maximize the work output of its constituent processes. जो प्रोसेसेस होता है जहाँ वर्क प्रोड्यूस होता है, अगर मैक्सिमम वर्क प्रोड्यूस होगा, एंड ड्यूरिंग द प्रोसेसेस इन व्हिच वर्क इज कंज्यूम्ड has to be, that amount of work that is consumed during those processes has to be least, and amount of work that is produced during some part of the cycle should be maximum. So maximum work produced hona hai and the least amount of work consumed hona hai, then only the net work output of heat engine will be maximum, and efficiency, which in turn efficiency will also be maximum. Network output agar maximum hoga तो efficiency will be maximum. So these things are possible only when the processes are reversible. All the processes that make up the cycle are reversible. If all the processes that constitute the cycle are reversible ones, then only the efficiency and network output of the reversible cycle will be maximum. Because in case of a reversible process, the maximum work is produced and the least amount of work is consumed. Obviously, the network output will be maximum if the processes processes are reversible, then the network output and efficiency of the resulting reversible cycle will be maximum. And many more reversible cycles are there, but the best known reversible cycle is Carnot cycle. Carnot cycle is nothing but the best known reversible cycle. And these reversible cycles are not practical cycles. They are only ideal or theoretical cycles, and they provide a model to which all the actual engines approximate. That means whenever we compare the performance of actual engines, we compare with that of the reversible cycles. Otherwise, the reversible cycles are not actual cycles and they are ideal cycles. So but they provide a starting point for analysis, and they provide the maximum limit on the performance of actual engines. The efficiency or work output of any engine, actual engine, heat engine, cannot be higher than that of a reversible cycle. That we will study later on while studying Carnot theorem and its corollaries. So any theoretical engine, any theoretical engine, theoretical heat engine, theoretical heat engine that operates on Carnot cycle is called Carnot heat engine. Carnot heat engine. Carnot heat engine. So this is Carnot heat engine. You know, Carnot cycle actually Carnot cycle जो कि एक रिवर्सिबल साइकिल है, consists of two reversible isothermal processes, two reversible isothermal and two reversible adiabatic processes. Two reversible isothermal and two reversible adiabatic processes. That's the most important thing. So Carnot cycle is an ideal or theoretical cycle, because reversible processes are not possible in nature. They are just ideal processes. They are just ideal processes, because you can't eliminate the all irreversibilities. The complete elimination of irreversibilities in a process is not possible. So there the things are, those cycles are, or those processes are ideal processes, and the resulting cycle is also ideal or theoretical cycle only. It is not possible to achieve a Carnot cycle in practice. So two reversible isothermal and two reversible adiabatic processes, and that means first one is, so suppose this is the Carnot cycle, and Carnot cycle can be, you know, this Carnot cycle can be executed by certain amount of gas enclosed in a piston cylinder arrangement, or by a steady flow system. We have already studied the steady flow system. Example of a steady flow system is steam power plant, where boiler, turbine, condenser and pump, you know, those are four components of steam power plant, and that constitutes a steady flow system. So that can also work on or operate on Carnot cycle, and also if certain amount of gas is enclosed in a piston cylinder arrangement, and that can also operate on Carnot cycle. So first thing is, you know, first we knew that it consists of two reversible isothermal and two reversible adiabatic processes. You know, in any cycle there is an expansion part where work is produced, and any reversible cycle or any cycle there is some expansion part during which some work is produced, and a compression part during which work is consumed, and always the net work output is positive in case of a heat engine. So you see, this is the process. These are the processes in the Carnot cycle. You see, first one is a reversible isothermal process. A certain amount of gas is enclosed in piston cylinder arrangement. Suppose initially the state of the gas was at state 1 and the temperature of the gas is at Th. You know, and the cylinder head is in close contact. Here piston cylinder arrangement, here the cylinder head is such that it can be removed sometimes, and it can be replaced by the these thermal energy reservoirs can be replaced by insulation also. But in this first process, that is an isothermal expansion process, what happens, the cylinder head is in contact with a thermal energy reservoir or source, high energy thermal energy source. Actually, you know, thermal energy reservoirs are two types, from which the heat is taken is called source, and to which heat is rejected is called sink. That we have already covered. And suppose this is the gas which is enclosed in cylinder, and if this gas expands slowly, you know, all these processes will occur slowly, so that these processes will occur in a these processes will be quasi equilibrium processes, and it will occur these processes will occur slowly, so that they can be considered as reversible processes or quasi equilibrium, internally reversible processes. And if the piston is assumed to be frictionless, that means they can be no irreversible defect is there. That means the complete process can be assumed to be reversible process. You see here, the temperature of the gas initially is at Th. When the gas is inside this cylinder, the temperature is this is at state 1. If the gas expands slowly, expands means its volume will increase. So if the gas expands slowly, then what happens? That means this is the system and these are the surroundings. When can the gas expands? When the gas expands means it does some work upon the surroundings. It will move from this point to this point. So that means here some amount of work will be delivered by the system. Some work will be produced. And how can this work come from? Where does this work come from? Obviously, its internal energy will decrease. When the gas expands means when the gas does some work on the surrounding means its internal energy decreases. According to Joule's law, we know that the internal energy of a gas, ideal gas, is a function of temperature only. So when the gas moves from state 1 to state 2, its temperature decreases by an infinitesimal amount. That is suppose process 1 2. You see, process 1 2 ये होता है रिवर्सिबल isothermal process. How does it occur? We'll study this. So you see, when the gas moves from this state to this state, its temperature obviously decreases because some internal energy is lost, and that loss in internal energy is converted into work output. Work करने के लिए energy चाहिए. So how can this work be produced? Only at the expense of internal energy. When the temperature of this gas decreases by an infinitesimal amount dt, when the temperature of gas, because it moves slowly, so temperature decrease is very less. Temperature decreases by an infinitesimal amount dt. So temperature decreases by a small amount dt. We know that when there is some so this is temperature decreases by infinitesimal amount dt. When the temperature decreases and already the source is at temperature Th, obviously here some difference is there, because this is less than the temperature of the gas at state when it moves from state 1 to state 2 decreases from TH. So obviously it is at a higher temperature than this one. Obviously the difference is dT, but some difference is there, means some heat transfer will take place. So heat transfer takes place from this to this, and after some time again the gas temperature attains its initial state, because here it is drops by dt, but once the heat is transferred from energy source which is at TH, will slowly but slowly the temperature will again return to its initial temperature, that is TH. And we can consider that during this whole process 1 2 temperature remains constant at TH, and since the difference of temperature during this whole heat transfer process is never more than dt, during the whole process 1 2 temperature difference between the source and this system is never greater than dt, an infinitesimal amount. So we can consider this as a reversible process. Of course we have to assume that the piston is frictionless. So that means the process, two important things: one is process 1 2 is reversible and it is isothermal, because the temperature of the system remains constant during this process. So next is, once the system reaches at state 2, now the energy source is replaced by an insulation. Energy source is replaced by insulation. Energy source is replaced by insulation. And now if the gas expands slowly, means your temperature will decrease from TH to suppose TL, and the system moves from state 2 to state 3, because if insulation is placed in the cylinder head, means no heat transfer can take place. Now this is an adiabatic process. This is an adiabatic process. So there is a drop in temperature from TH to TL. So then the system reaches at state 3. So this is an adiabatic expansion process. Process 2 3. Process 2 3. This is a reversible adiabatic expansion. Reversible adiabatic expansion. This process 1 2 and 2 3 constitute the expansion part of the cycle. Now that there is a drop in temperature from TH to TL, and next comes the compression part. So first compression that takes place is when the piston is pushed inward. Compression means we have to do some work from outside, so we have to provide some work from outside. So whenever the piston is pushed inward, and when the compression takes place, temperature of a system increases. Suppose during the process 3 4, so when we push this piston inward, and during the compression process temperature suppose increases by an infinitesimal amount dt. Here the temperature is TL, because during the process 2 3 temperature decreased from TH to TL. So here when we pushed inward, already the gas was at temperature, here at state 3 the temperature of the gas was at TL, and when we push, temperature increases by suppose dt. When there is an infinitesimal increase in temperature, suppose dt, then what happens? Some heat will be rejected, because it's the gas temperature will be a bit higher than the sink temperature, which is at TL, and then heat will flow from this to this, unless and until the temperature of the gas is temperature of the gas decreases once again to TL. So during the process 3 4, we can assume that the process is isothermal and compression. This is a compression process and isothermal, and since the temperature difference between the sink and the gas never increases than the dt, that is an infinitesimal amount, we can consider this to be an reversible process, and this is a reversible isothermal compression. Work is consumed during this time. So this process is reversible isothermal compression. Then the last process is 4 1. So at state 4 the temperature of gas is TL. So once again the sink is replaced by in cylinder head is replaced by, here the cylinder head is in contact with insulation in place of sink. Here sink is replaced by insulation. So no heat transfer can take place at this state during this process, and this is an adiabatic process. And when we compress further from state 4 to state 1 to complete the cycle, obviously a compression will take place, and temperature will increase from TL to TH to return to the initial state. So this 4-1 will be, process 4-1 will be reversible adiabatic compression. Obviously the piston is assumed to be frictionless and or quasi-equilibrium process, slow process. So that means first process is reversible isothermal expansion, then reversible adiabatic expansion, then reversible isothermal compression, and 4-1 is reversible adiabatic compression. If we draw the PV diagram of this Carnot cycle is like this. During process 1-2, that is reversible isothermal process, QH amount of heat is added to the system, and the temperature of system remains constant at TH. And during 2-3, that is adiabatic expansion, temperature decreases from TH to TL and volume increases. This is PV diagram. So during expansion process pressure decreases. So 1-2 pressure decrease हो रहा है and volume increases. And during 2-3 also the pressure decreases but volume increases. Obviously during the process 1-2 temperature is constant as TH. Suppose let QH is the amount of heat added to the system during this process 1-2. And during this process 3-4, obviously a compression process, pressure increases but volume decreases, but heat is rejected. That amount of heat rejected is QL. And here this is 4-1 is adiabatic compression, during which increase in temperature from TL to TH takes place. And if the efficiency we calculate will be net, this formula 1 minus QL divided by QH, 1 minus QL by QH. And you see area under this process curve, area under PV diagram always represents work. So during this process 1-2, area under 1-2 represents the net work produced during the process 1-2, and area under 2-3 represents the net work produced during the process 2-3. ये जो area under 1-2-3 होगा, that will represents, if you calculate area under 1-2-3 projected on volume axis, this will represent the work output or work produced during this isothermal processes. But during this process 3-4 and 4-1, that whatever work is produced, that will be, suppose this area will represents the work input, and this total area represents work produced during this expansion part of the cycle, and this yellow area will represents the work input or work consumed during the compression part of the cycle. So this area under this included part 1, 2, 3, 4, 1. So 1, 2, 3, 4, 1, ये पार्ट वाला, ये वाला जो इंक्लूडेड एरिया ऑफ द साइकिल, ये वाला एरिया 1, 2, 3, 4, ये एरिया से अगर ये एरिया माइनस करेंगे तो ये एरिया 1, 2, 3, 4, 1 represents the net work output of the cycle, So this is all about Carnot cycle. It is a reversible cycle and it consists of 4 processes. 2 processes are expansion and 2 processes are of compression type. One is isothermal expansion and 1-2 is isothermal expansion, where temperature is constant at a higher temperature TH, and during the 2-3 there is a decrease in temperature, and this 2-3 process is adiabatic expansion, and 3-4 is isothermal compression, and 4-1 is adiabatic compression. Here during the process 4-1 there is an increase in temperature. So thanks for watching.